Hello and welcome to Critical Thinking Lecture 4. Today we're going to be discussing visualization, broken down into, of course, as always, beginning with meditation, then a bit of the in-back, some chunking strategies. Hopefully this won't frighten you, but a brief discussion about algebra and geometry and why it's useful for visualization, as well as some discussion of cognitive habits and abstractions. So we'll start with the room. This is a new one. A new meditation technique, that is. So I'll walk you through it this time, and then later I'd like for you to do it on your own. But for now, close your eyes. Imagine a room when you're comfortable in, when you've been comfortable in before. And I'd like for you to identify 9 distinct locations of the room, like a door or a couch, a windowsill. I want you to carefully, in your mind, place each of the following items in one of the identified places in the room. A picture of a cat, an apple core, your tax returns from last year, your tax returns from the year before last, 7 M&Ms, a pencil, a pen, 3 crayons, and 2 markers. Pause the video and do that, and then wait about 1 minute before returning. As for me, I'll continue on. First, back to the in-back. I'd like you, now that you're calm and relaxed, to navigate to this page here where you can play the dual in-back game. I'd like for you to play 3 rounds of the game, and I want you to set it to 4 back. So you can control the settings up at I believe the top right corner of the screen. I believe the default is either set at 3 or 2. Go ahead and set it to 4. And enjoy. It's not going to be fun, but I think you know that by now. But when you're done, come back. I'll continue, assuming you've done this, over to 7, or plus or minus 2, and chunking. So what is this? As I mentioned before a couple of times, sort of a theme here, with finite memory capacity. We're able to remember things without much difficulty to the tune of maybe 7 items, random items, plus or minus 2. So by random here, I just mean there's no connection among the items. It's not like numbers, right? There's not a pattern you can use to generate more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Those are not random. But like the string of 9 items I gave you a moment ago in the room meditation exercise, random. Okay. Now, roughly speaking, experimental research suggests pretty strongly that people can remember about, on average, 7 plus or minus 2 random items. It's important here. Just note that items need not here be restricted to conventional things you would count, as evidenced by the room meditation. Now, there's this thing we do sometimes that makes it easier for us to remember stuff. It's called chunking. Think about your phone number. Most of us can easily recall the numbers in the phone in a phone number, and they are grouped into like 3 little sets of numbers. That makes it easier to remember them. There are hyphens between them, and those hyphens group the numbers into chunks. Look, I'll illustrate just in case you don't believe me, although I don't know why you wouldn't at this point. Try to remember this string of numbers. Okay, pause the video. Can you recite the numbers? Give it a shot. Were you right? Maybe. I bet you had a difficult time doing it even if you were, and most of you probably weren't. Let's try another. Go for it. Pause the video. Can you recite the numbers? Was this your answer? I bet even if you didn't get it right, you had an easier time, and I suspect more of you got this one right than the preceding. Why? Chunking. Check it. Group, 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 group. These groupings become the new items to remember. You'll have an easier time remembering 7 plus or minus 2 such groupings, as long as the size of the groups remain less than 7 plus or minus 2. This is to say that we can remember 7 plus or minus 2 random items without much difficulty. But the term items can mean groups, right? For instance, I could ask you to remember a list of people's names, But also I could ask you to remember a list of countries, and countries are composed of people, right? So there are different levels of abstraction we can take when we're thinking about chunking and how it works and can work effectively for us when we're attempting to remember things. This is sort of a species of the more general divide and conquer strategy, which I've mentioned a couple of times. It involves breaking down complex information into smaller, digestible, less complicated information nuggets. Trademark, that's my word. Let's see the strategy in action a bit more by going to the NBAC again. Okay, once more, this time with fervor. Try it out and play the game. This time I want you to attempt to use a chunking strategy to make it easier. And if you have been doing that, just practice getting better at it. And think about how it works and think about how you can explain it to other students, because I'm going to ask you to when we meet. All right. Now, to the part of this lecture that I'm sure you've all been waiting for, algebra and geometry, right? I know what you're thinking. Algebra? Geometry? No. Maybe you didn't hear me. No. I don't blame you. I really don't. The way these topics are taught in the U.S. makes them so boring. I did not like math in middle school. I think I started one, like the beginning of the first week of a math class in high school before I dropped out, and I did not like it. It was so boring. It also makes it seem inapplicable to your life. Who cares how many bananas you would have given some complex formulae or whatever? I don't even know what the plurals of formulas is. Like, it's all confusing unnecessarily. So I think it's the poorly taught is the problem. Let me school you something though. These topics haven't always been so boring, and they don't have to be now. In fact, as a matter of history, they weren't always topics. And I think a very brief exploration of the background and motivation for why we have algebra and geometry might help you see why it's perhaps more important than is let on in traditional education. So let's start with algebra. What is it? Strictly speaking, roughly strictly speaking, it's a formal study of a special set of mathematical symbols and relations among them. In grade school, you learn things like 2 plus 3 equals 5. This area of math is called arithmetic. Later, you learn to solve equations like this. X is a variable, it could be any number. X plus 3 equals 5, we know the answer to that. You also learn to solve equations like x plus y equals 5. Or x plus y equals z. So like sets of equations, various numbers could fill in these variables here. This area of math is called algebra. There are different levels of algebra. In the most advanced sort of algebra, which you get exposed to in upper level college, you solve equations not just that look like this, but which also abstract over the relations among things, among numbers. So for instance, you might solve things that look like this, or you might fix on particular numbers, systems that look like this. And in many other cases where one could be replaced by any number. Generally speaking, you study variables over relations between things as well as the variables over the things themselves. This is like high-level abstraction. Okay, that's a brief overview of what algebra is. What's geometry? Formal study of size and shape and relative position. Let's make this a little more concrete. This theorem, attributed to Pythagoras and proven by Euclid, can be represented algebraically as a squared plus b squared equals c squared. It's the Pythagorean theorem. It represents a relationship between the lengths of sides of any triangle. Prove it. And don't use algebra. In fact, Euclid didn't use algebra because algebra wasn't a thing when Euclid was writing. Check this out. This is a great video. V. Hart here will give you an illustration of how this might work. V is a mathematician who uses creative, often geometric means to illustrate important mathematical concepts. I highly recommend V's channel here. In the event, Euclid wrote the Elements centuries ago. He basically nailed geometry with a few caveats a couple of hundred years ago. Algebra, though, came much later, to Europe at least, and it was a watershed moment. Things really became interesting when Descartes, is the guy who said, "I think, therefore I am," realized that algebra and geometry were basically the same thing. Check it. This is Descartes. This is a bunch of French townies at the time. This is him realizing the relationship. You're all like part of a grid. For real, man. It was great. And this is what he came up with. This is why, incidentally, we call this grid, I'm sure you've seen in class, the Cartesian plane. It's named after Descartes. This is a relationship between numbers or points and space. And we often talk about algebraic expressions with like various variables and some numbers in them with pluses and minuses as corresponding to curves or shapes on the line. You probably have seen this with your TI, whatever the numbers are now, these calculators. You can like make pictures with numbers, right? Or like make pictures with equations on the Cartesian plane. Check it. That's it, right? That's the relationship. Geometry meets algebra. It's basically, this Cartesian plane is basically a bridge between abstract symbols and shapes. That is, between algebra and geometry. All right, now, on to the more interesting stuff. I mean, I don't actually think that, but maybe you do. Cognitive habits and abstraction. Let me ask you this. Consider this argument. If John is bald, then John is happy. John is happy. Therefore, John is bald. Is this good? This is a good inference. If you accept 1 and 2, does 3 follow? No. This is a fallacy. It's called affirming the consequent. They call it this because it just means affirming the thing after the then in the if-then sentence, which is called the consequent. It has the form if A then B, B, hence A. And this is always a bad inference. And now you have a name for it, so you can see it in the wild, and you can spot it, and you can avoid it. Now, I have a question for you on the next slide that will sort of combine the insights here, especially this relationship between algebra and geometry and also the cognitive habits discussion. But don't rush to answer. Think about the form of the question, and note that I'm looking for a logical solution, okay? Here it is. Larry is married, but Nick isn't. Larry is looking at Mary, and Mary is looking at Nick. Is someone married looking at someone not married? Go ahead and pause the video now and think about this for a bit. Be sure about your answer. Like, think about your answer before you start back. Okay, I'm going to start now. Most say this is the answer. Most are wrong. Consider. Mary is either married or not. If married, then since Mary is looking at Nick, who is unmarried, someone is looking at someone who is unmarried. If unmarried, then since married Larry is looking at Mary, someone married is looking at someone unmarried. Either way, the answer is yes, since Mary actually is married or not. And that's the end. We'll talk more about this in class. See ya!